Hello, everybody. In this video, we're going to learn about the chain rule and directional derivatives, specifically in the case of multivariable functions. Mostly, to be honest, we're interested in directional derivatives, but the chain rule is going to prove to be an invaluable tool to help us derive a formula to calculate a derivative of a multivariable function in any direction. Right, so the ultimate goal has to do with calculating partial derivatives, kind of. So given a function, a multivariable function, so one with two inputs and one output, we could write this function as f of x comma y is equal to z. We've learned how to calculate partial derivatives, and we think of this as rate of change of a function as you go along the x direction or the y direction. So we've written df dx, or partial f partial x. We think of that as rate of change of the height of the function, or the value f, in the x direction. And as you move in a direction parallel to the x-axis, how quickly is the value of f changing as you change x? And similarly for y. Right, we can calculate the partial derivative df dy. And again, that's the rate of change of your function f in the y direction. And we know that this can be very helpful to help us calculate tangent lines going in different directions. But what we'd like to know, right, so our ultimate goal, this is really the background, the ultimate goal is to calculate the rate of change. So we're going to calculate the rate of change of the function f in any direction, not just the directions parallel to the x and the y-axis. So if we had to give a geometric interpretation of what we're doing, we can think of this in terms of tangent lines. And so let me go ahead and draw an x, y, and z axis. And then I'll draw a function on this axis. All right, so again, I always like to draw a picture of a hill here. All right, we have tangent lines going in the x direction. All right, so at some point, you might pick some point on your curve. You might figure out how quickly the height is changing as you travel in that direction. You know, maybe you're going downhill a little bit from that particular point. If we look parallel to the y direction, and from this point, maybe we're kind of going around the hill, and there's a certain rate of change of the function in that direction. We're now interested in all the intermediate directions. Right? So if you do some combination of movement in the x and y directions, for example, if you were to move mostly in the y direction, but a little bit in the x direction, right? If you were to move in, I don't know, we'll call this direction indicated by the vector u. Maybe that's the vector u1, u2. And if we're traveling in this direction, what's the rate and change of the height? In other words, what's the slope as we travel in this direction? And to give us a different perspective, if I had to do a top view of the same situation, right? Imagine you're looking down along the z-axis. And so for the top view, z is kind of coming out of the screen right at you, and here's y and here's x. And looking at our graph from the top, well, we're kind of looking down upon a hill. And so this is sometimes called a contour map. And maybe this is what it looks like from above. And we know what happens if you go in the x direction. And we know what happens if you go in the y direction. And we know how to calculate those. Those are partial derivatives. Our big question today is, what if you go in some intermediate direction? How do you calculate that precise rate of change in some direction u? And this is our ultimate goal, but before we find the formula, we need to talk about the chain rule a little bit. The chain rule is hopefully familiar to you from a first course in differential calculus. So let's say from calculus 1, for example, you might have maybe f, right? So f is, I don't want to say f, no. Let's say I have a function, no, I do want to say f. Let's say I have y is a function of u, but u, in turn, is a different function of x. In other words, you have y is a function of u is a function of x. In other words, you can think of y as a composite function, right? F of g of x. And what happens if you want to calculate the derivative of y with respect to x? Right? What is dy dx? Right? Especially when you have this intermediate variable u in there. Well, the way you can calculate that is find the derivative of f with respect to u times the derivative of u with respect to x. Right? For example, maybe you have y equals f of u, which is, let's say, maybe u cubed, and u equals g of x. Let's say that's sine x. And how could you calculate dy dx? And dy dx is first the derivative of f with respect to u. The derivative of u cubed is 3u squared times the derivative du dx. The derivative of sine x is cosine x. And if it feels a little bit strange to see that variable u in the final formula, you could rewrite this as 3 times sine of x squared times cosine of x, right? Equally valid. Oftentimes you might just skip the u, and you might say, equivalently, you have y equals sine of x cubed. You've probably done enough calculus problems to immediately remember how to apply the chain rule mentally without thinking about an intermediate variable u. Dy dx, you'd write that as 3 times sine of x squared times the derivative of the inside, which is cosine x. Both ways you get the same answer. It's really just the same process. One just uses an intermediate variable. Now, one thing I would like to do is to draw a little diagram. We don't really need a diagram here. Over here on the left side of the screen, we have y, which depends on u, and u depends on x. I'd like you to just keep this little diagram in the back of your mind. Right? Y depends on u, the arrows indicate dependence, and u depends on x. Right? As x changes, the value of y changes as well, but it depends on the change that x creates in u and the change that u creates in y. And so I like to think of this chain rule, kind of like a chain rule diagram. Right, so here, again, we have y depends on u, which depends on x. So when we want to calculate the change on y as x changes, well, we have kind of two changes as we go down this diagram. We have dy du and du dx. And these multiply together to give us the total change. Right, so dy dx is equal to dy du, or df du, if you prefer, times du dx. Now, the chain rule for multivariable calculus, it's pretty easy to look up a proof of this, but again, my main goal is to talk about directional derivatives. So I'm just going to state here the chain rule for multivariable functions. I should say maybe rules, because it could take different forms depending on the relationship between the variables that we're looking at. So the chain rules for multivariable functions. For example, we might have z is a function of x and y. And we've seen a lot of those recently, but perhaps x and y themselves are also functions of some other variable. And so maybe x is a function of t, and also y is a function of t. Call that h of t. In this case, the diagram is a little bit more involved, not too bad. Right? Z depends on two variables, x and y. X and y themselves both depend on the variable t. So as we change the value of t down at the bottom of this diagram, that's going to indirectly change the value of z. And our question in calculus is, well, how much does it change that value? Well, there's lots of different derivatives we could calculate here. For instance, we could calculate, on the left side, we could calculate dx dt. That tells us how changing t changes x. We could also calculate dy dt. Right? These two functions g and h, those are single variable functions. So we can calculate their derivatives using the rules from good old Calculus 1. At the same time, z is a function of x and y, and to see how z changes as either x or y change, we can calculate some partial derivatives. So for example, dz dx, partial z partial x, and dz dy. Right? There are all these different related rates of change. So the big question is, think of z as indirectly a function of t, and what if we want the formula that will allow us to calculate dz dt? Well, we take our inspiration from the chain rule diagram in Calculus 1, right? As we go from y to x down at the top, to figure out the total effect that changing x has on changing y, we multiply the derivatives going down that chain. Right? So for example, z is affected by t through the variable x. Right? So we have part of this formula is going to be dz dx times dx dt. Another part of this formula that again looks like a case of the chain rule from Calculus 1 is that changing the value of t changes z through y. So that's going to give us another term, again multiplying the derivatives along that part of the chain in the diagram. We'll have dz dy times dy dt. Now what should we do with these two quantities? Well, it turns out that we just need to add them together. They each contribute kind of independently of each other. So the total change in z is going to be the sum of the contributions of the changes along each one of these chains, or each one of these paths from z down to t. All right, let's go ahead and do an example of this. So let's go to the next page. Let's switch and let's do an example. Let's say that we have z is a function of x and y. Let's make this x squared y cubed. Let's furthermore say that x is a function of t. Maybe that's t squared plus 3. maybe y is also a function of t. Maybe this is 5t plus 4. And our question is, what's the derivative of z with respect to t? In other words, as t changes, how does that affect z? When doing this kind of problem, I always like to draw this kind of dependency diagram. Z depends on x and y, each of which depends on t. So my formula, again, is dz dx times dx dt plus dz dy times dy dt. So next we'll calculate each one of these derivatives. And first, let's look at the partial derivative of z with respect to y. So let's get my colorful pointer here. So if we're doing a partial derivative, this first term, x is our variable and y is like a constant. So the derivative of x squared times y cubed, right? Y cubed is like a constant that just comes along for the ride. This will be 2x times y cubed. The next term, so that's this first term here. The next term, dx dt, we're finding the derivative of t squared plus 3. This is just a single variable problem. We could write that as 2 times t. So that's our next derivative. Plus, now we need to calculate dz dy. So again, this is a multivariable problem. Y is the variable, and x is the constant in this scenario. So we have a constant times y cubed, and the derivative of the constant times y cubed is that constant times 3y squared. I'll move the 3 out in front. I'll get 3x squared y squared times the derivative dy dt. And again, a single variable problem here. The derivative of 5t plus 4, that's just 5. And there we go. That's the whole answer right there. If you want, you can combine like terms that might make it look a little bit nicer. You can say 4xy cubed t plus, so we've got 15 x squared y squared. And if you really want to, and if you really only want t's in there, you could take the functions for x and y and insert them in this equation every place you see an x and a y. And so here, let's see, I've got 4 times t squared plus 3 times 5t plus 4 cubed times t plus 15 t squared plus 3 squared 5t plus 4 squared. I don't know if that really gives me any additional insight, and I certainly don't want to expand that out, but you could. And it's nice to know that you could convert everything to an expression with just one variable in it. All right, so that's a good example, but we should do some other examples as well. And so I'd like to show you a different variation on the chain rule. Remember, we said there's going to be more than one chain rule because there's lots of different relationships that variables could have with each other. So the other chain rule, which I tend to see a lot, and so let's have a chain rule for a function. Again, z is a function of x and y, and x and y can be functions of other variables. In particular, I'm interested in something called polar coordinates. Right? X and y can be represented as functions of other variables. There's more than one way to describe the location of points in a plane. And so the relationship that I'm particularly interested in, if I have a point, x and y, I can describe the location of that. Right? In xy coordinates, what does that really mean? Right? Xy coordinates means you go over x units, then you go up by y units. But sometimes it might be more natural to think of this as starting at the origin, rotating by some angle theta, and then going in a straight line by some distance, which I'll call r. Think of r as the radius and how far away that you move. Right, so you can also specify this location in polar coordinates using the values r and theta. And these values are all very closely related, right, by a combination of the Pythagorean theorem and basic trig identities. Right, so in particular, you might recall that cosine theta and sine theta can be calculated as different ratios of sides of this triangle. Right, the width of this triangle is x and the height of this triangle is y. The sine of an angle, right, that's the opposite side divided by the hypotenuse, and the cosine is the adjacent side divided by the length of the hypotenuse. We can turn each one of these into formulas for x and y in terms of r and theta. And so we could write x equals r times cosine theta, and y equals r times sine theta. Going back to our formulas up here, right, so we have z as a function of x and y. You can think of x and y as being specified in terms of some radius, some distance from the origin, and some angle theta, some angle around the origin. And so you might ask yourself the following question. And if you start at some point, maybe I'll draw my three-dimensional graph here. So I've got my x, y, and z axis. I'm going to go ahead and draw the hill like so. Right, instead of moving in a straight line, you might ask yourself the following question. And so let's say I'm sitting at this point on the graph. I'm going to go ahead and draw kind of the shadow of that point on the xy axis. And so this is some point which lies above this other point in the xy plane. And we already know how to calculate some of the partial derivatives here. Right, if you move along the x-axis, right, you're moving in this direction away from the point. I'd ask how much the height of the function changes. Same thing for moving along the y-axis. As you're moving in this direction, how quickly is the height changing? Thinking of the function in this way, right, in terms of r and theta, can allow you to think of this problem in a new and exciting way. What if, instead of moving along the x direction or the y direction, or even indeed moving in any one particular direction, what if you started moving on a line away from the origin? Another case, or in other words, what if you're moving along a radius pointing away from the direction? You might want to ask yourself that. How quickly does the height of this function change as you move away from the origin? Or you might ask yourself, as that angle changes, right, this angle theta, as you move around the origin, how quickly does your function change? Right, so as you move in this direction, as theta changes, how quickly does your function change? Both two perfectly valid questions. So you might ask yourself, can we possibly calculate the change in the function as r changes? Or what's the change in the function as theta changes? And in this case, we basically need another version of the chain rule. Our diagram in this case, you can think of this as f, or you could also think of this as z. It's equally fine. Write them both in right here. You can think of the function z as depending on x and y. Maybe your function f is expressed in terms of x and y, but x and y both depend on r and theta. So we have more arrows to draw. X depends on r and theta, and y depends on r and theta. So this is our diagram here. This is the most complicated one we're going to look at in this video. Again, it asks you some kind of natural geometric questions. So we'd like the chain rule, which corresponds to this diagram, to answer these questions. How do we calculate or measure these rates of change? And thankfully, the same idea we used for the previous chain rule applies here as well. Let's go ahead and rewrite that chain rule. Let's rewrite that dependency diagram. We have z depending on x, leaving lots of space here to write my derivatives, depending on y. X depends on r, x depends on theta, y depends on r, and y depends on theta. Again, like the previous example, we can calculate lots of partial derivatives. Okay, we can calculate dz dx, and because we're checking the change from z as x changes, we can calculate dz dy. We can also calculate these derivatives here as well. It seems like a lot of derivatives, but the formulas are pretty easy, so it's not so bad. As x depends on r, we could write that as dx dr. You'll notice that I'm using the partial symbol here. This is because x can be expressed in terms of two variables, and thus the partial symbol is more appropriate in this case. You can also take a look at the change in x as theta changes. I look at the change in y as r changes. I can look at the change in y as theta changes. So we have a lot of partial derivatives here. Now let's actually write out maybe an example formula that'll, actually no, before I write out the example formula, I haven't written the chain rule yet. So if we want to calculate something like dz dr, we're going to follow the similar procedure that we followed last time. We're going to take a look at the ways in which z depends on r. It's indirect, and there's two different ways z depends on r. Right? Z depends on r through x, and also z depends on r through y. So along each one of these chains of arrows, we'll multiply together the derivatives, and we'll add the results from each one of the chains. And so the chain rule for dz dr will be dz dx times dx dr plus dz dy also times dy dr. And the same line of reasoning will let you derive a chain rule for dz d theta. How does the height of the surface change as you rotate around the origin? Well, we're going to look at the dependence of z on theta. And again, it's indirect. Z depends on theta through x. So multiply those derivatives together. And z depends on theta through y. So multiply those partial derivatives together. We'll add up the contributions along each of the chains. So we have dz dx times, that looks a little bit like a 2, times dx d theta plus dz dy times dy d theta. Right, so those are our chain rules, and you would have similar looking chain rules even if you weren't using r and theta. If you're using any other two letters here, right, it could be r and s or t and u. You get similar looking chain rules in that case. Let's go back to our previous example just to see how these look in action. Right, let's say we have z, again, a function of x and y. Let's make that x squared y cubed. Again, we know that x is r times cosine theta, and y is r times sine theta. And let's say we want to calculate the formula for dz dr at a given point. So what we could do is, let's see, chain rule for dz dr is equal to, see, first dz dx, and so x is your derivative, it'll be 2x y cubed times dx dr. And so we're finding the derivative of this expression with respect to r. R is your variable, which means theta is a constant. And cosine theta is, well, cosine of a constant, which is still a constant. Maybe an unusual looking constant, but this is r times a constant. The derivative of r times a constant is just that constant, cosine theta. Plus, the second part of our formula now, dz dy times dy dr. See, the derivative of this with respect to y is 3x squared y squared times dy dr. For similar reasoning here, right, r is a variable, so theta is a constant, sine theta is a constant. We have derivative of r times a constant. Derivative is just that constant. So that is the formula. And again, if you really wanted to, you could substitute away these x's and y's for these expressions with r and theta, if you so desire. Might as well also calculate dz d theta while we're at it. And fortunately, we can actually recycle part of our work from before. Both these formulas contain the partial derivatives dz dx and dz dy. So I can actually write 2xy cubed, leave a space, dz dy is 3x squared y squared. And now, in this first empty set of parentheses, we need the partial derivative dx d theta. And so we look at our function of x, and now we're treating r like a constant, and theta is the variable. The derivative of cosine theta is negative sine theta. So the derivative of a constant times cosine theta is negative constant times sine theta. Similarly, when we need to calculate dy d theta, right, theta is now our variable, and r will be treated like a constant. The derivative of a constant times sine theta is that constant times cosine theta. Right, and there you go. And once again, if you so desired, you could replace x and y with these functions of r, cosine theta, and sine theta, and plug in any values that you have. And that is how you calculate a chain rule for a multivariable function. But as you might recall from the beginning of this video, let's flip all the way back. What we're really interested in is something called directional derivatives. So far, we've learned about something called partial derivatives. Right? Partial derivatives give you rate of change in a specific direction, along the x-axis or along the y-axis, if you just change a single value. But what we really like to do is calculate the rate of change in any direction. And it turns out, perhaps somewhat surprisingly at first, that the chain rule will actually help us to do that. And as usual, I really like to think of these things geometrically. So now, again, we're going to shift our focus to directional derivatives. So first, let me go ahead and define this. The directional derivative of a function of more than one variable, f of xy, in the direction let's say we have a unit vector, u, which I'll write as having components u1, comma u2. Again, by u, I'm going to mean a unit vector. Informally, let's think of this as the rate of change, well, I guess formally too, I'll write down the definition, but this is the rate of change in the function along this direction. So this is the rate of change of f along this direction. Now, how do we calculate the rate of change? Well, we have a formal definition of a derivative. Right here, the symbol for the directional derivative is going to be a d with a subscript vector u. So the derivative of this function, I usually like to define this as some kind of limit. We think of 2 points being kind of close to each other. I'm going to be a little bit odd and say the limit is t goes to 0 of f of x plus t times u1. And I'll draw a picture explaining this in just a moment, comma, y plus t times u2, close parentheses, minus f of xy, all divided by t. Now, let's take this definition apart and try to figure out what this means. Right? And to help us with that, I'm going to go ahead and draw kind of another top view picture. This is a top view of the graph of the function f. And so imagine you're looking down along the z-axis. The z-axis is coming right out at you. And here's the x and y axes. And once again, we're looking down upon a hill. And so think of this as like a contour map, right? So the high point is in the center. Then the function just keeps decreasing along each one of these lines. Let's say we want to calculate the derivative at this point right here. We want to calculate the derivative as you move along in this direction. So not quite the x-axis, not quite the y-axis, but a combination of those two. Right? And how might you go about calculating the derivative or the slope in that direction? Well, what did we do in Calculus 1? We would create 2 points which were relatively close to each other. So you've got your first point, x comma y. That's pretty legible because I'm writing right on top of the graph here. And so this point right here is x comma y. We want another point which is really close to this point. Let me calculate the difference quotient. So what is this point going to be? Well, we're going to start at x comma y and add some small amount of the vector u. And I'll call that small amount t. T times the vector u. And as t gets closer and closer to 0, as we let t get smaller and smaller, we're adding a smaller amount to the point xy. So as t gets smaller, this point here is moving closer and closer to that point there. And this expression, this xy plus t times the vector u, right? What is that? That exactly matches this expression right here. Right? If you actually carry out the addition here, you have x comma y plus t times the vector u1 comma u2. You do your scalar multiplication, and then you do some vector addition, and you're left with exactly this expression here. So this is the official definition of the directional derivative. Again, whenever possible, I like to reason by analogy to what we've done in Calculus 1. Think of 2 points moving closer and closer to each other. And the closer and closer is expressed by this quantity, getting closer and closer to 0. As t goes closer to 0, the height, this f component, moves closer and closer to this height. All right, that's fantastic. But it doesn't really give us a way to calculate it, right? And ultimately, this is calculus. We would be able to calculate rates of change. So we're actually going to use the chain rule to give us a different way to think about this problem. So let's head over here. Again, the goal is we're going to use the chain rule to, let's say, evaluate directional derivatives. Or at least it's going to give us a way of deriving a formula. Derivatives. So we're using the chain rule to evaluate directional derivatives. Now the key is really this picture that we drew over here. Right, think about this blue vector that we're traveling along. We're really interested in learning how the height changes as we travel along this line, which points in the direction of u. So let me go over and maybe copy over this picture again. It's a good picture. Oh, it's a useful picture. All right, so here's, again, the top view of what we were looking at before. If you're happen to be copying this down in a notebook, it's probably a lot easier for you to flip back and forth from one page to the other. All right, so starting at this point, right, we're traveling along this vector, along the vector u. We can also think of that vector u as part of a longer line that passes through the point xy that we're particularly interested in. And so again, we can think of, right, the derivative is changing, or the derivative is calculating the change in this function as we travel along the line through the point xy in the direction of u. So let's write down the equation of that line. Right, so the line L of t, right, is going in the direction of u. I could write that as u1 comma u2 times t plus, think of the point xy as kind of like the base point on this vector. And again, think of this as a fixed point on the line. And if you think about the big function f of xy, these are variables. But if we're just thinking about this line L of t, right, t is the only variable here, and we're keeping x and y fixed throughout this discussion. Right, so we're really interested in the directional derivative. Right, and before, right, we wrote that as, right, this is f of x plus t times u1 comma y plus t times u2 minus f of xy all over t. Oops, I should have really put a limit as t goes to 0. So I'm going to go ahead and suppress that notation for a bit. But what we have here, it takes a moment to see, but we really have kind of a composite function here, right? Inside f that actually looks like the results of the function L of t. Right, so again, this expression right here, I can write that in a different way. I'm going to write a new function. Let g of t equal f of L of t. This gives you a point in three-dimensional space as you're traveling along this line. It's almost like a cross-section of this graph, right? Because the only values you can plug into f, because of the way this equation is set up, are those points which are on the line L of t. So we're taking points from the line and plugging them into our multivariable function f, and we get some kind of height along here. Right? The graph of g of t is really just going to be a small slice of the graph of this function. So since we're interested in the change of the value of f, right, as we travel in this one particular direction, along the direction u, what we're really interested in is actually the derivative of g, right? G is the function f restricted to movement along this line L. Right? If we define this, then right, the directional derivative that we're interested in is actually the derivative dg dt. And because we have the chain rule, we can actually calculate this without too much problem. Right? So this function g of t is a combination of f and L. Right? So f depends on two variables, x and y, and x and y here are both functions of t. So this tells us that we can calculate the directional derivative, right, using the chain rule. Remember the way the chain rule works, right? To see how this function changes, right, we're going to see how f depends on t indirectly. F depends on t through two paths in this dependency diagram. As t changes, it changes x, which changes f. And as t changes, it changes y, which changes f. So the derivative here can be calculated as df dx times dx dt plus df dy times dy dt. Right? And so how do x and y both change as functions of t? So we can calculate that using the expression L of t, because this is giving us our change in the x and y component as a function of t. Right? In this equation, x and y are kind of like constants. The change, dx dt and dy dt along this line, the change is given by the slope vector. So we can actually rewrite this. Right? As we move along the line L, right, how does a change in t change x? We're taking the fixed x value and we're adding t times u1 to that fixed x value. So dx dt is u1 plus partial derivative df dy times, well, as we travel along this line, right, how does the y value change? Let's move along this line. Again, along this line, we're fixing the point xy. I'm fixing this point right here. And then, as t changes, right, the base point is changing by this value u2. So this is u2 right here. Right, if it helps, another way you can think of this, instead of thinking of this as dx dt and dy dt, right? No, let's leave it like that. But remember, these are changes along the line in each of those coordinates as t changes. And the other great thing is there's another way you can write this. Let's go to the next slide. And so to calculate the directional derivative of f, And we just found that it was df dx times u1 plus df dy times u2. This actually looks a little bit like a dot product. Right? It's a product of two things plus a product of two things. We could write this as df dx comma df dy dot product with the vector u, u1 comma u2. And so it's like we're calculating a dot product with a direction that we're interested in moving in. Dot products have made yet another appearance. And here, this vector of partial derivatives, this seems to be pretty special, right? It's not something we've technically encountered before. We have seen something similar where we had df dx, df dy, and -1 as a vector in a different context. But the vector of partial derivatives, well, seems important enough that we should give it a name. And in fact, mathematicians do. They sometimes call this the gradient of the vector f. And so this upside down triangle is sometimes called the gradient symbol. Sometimes it's read as del. And so this is the gradient of f, or I like to think of it as the vector of partial derivatives. So in other words, what we've just explained is how to calculate the derivative of a function in any direction. In retrospect, it makes a lot of sense if you think about it, right? To calculate the derivative of a function in any direction, right, it's going to be some combination of the standard partial derivatives, right? And this is telling you exactly what combination of these two partial derivatives it is. Right, so if you move in a direction which is mostly along the x-axis, you'll get a larger value for u1 than u2, and that means it really depends on df dx. You know what, that sentence made no sense. Let's do an example, because you learn math by doing math. So let's say I want to calculate, for example, the derivative, the directional derivative of the function f of x, where f of xy is equal to, I'll take my favorite function, x squared y cubed, at the point x comma y equals, let's see, maybe I'll do the point 3, -1 in the direction, let's say v equals 2, 1. Notice I'm using a v here, and I'm doing that on purpose, as we'll see in a moment. Before we jump into calculations, I want to do kind of a top view of what problem this is. And so again, imagine you're looking down along the z-axis at some kind of a graph here. I have no idea what graph this looks like, but you know I like to draw the same graph. So there's our little contour plot. And here's the point. This is nowhere to scale. Let's say this is 3, -1. So maybe it's not the point 3, -1. I know that. You know that. I can't see that. Right, so this is the point 3, -1. Now, we could calculate the derivative in the x direction and the y direction. We know those are the partial derivatives, but we're really interested in the direction 2, 1. In other words, if you go over 2 on the x-axis and 1 on the y-axis, right, we're interested in the derivative in this direction. Right? And we've learned that we can write that as a combination of the values of the partial derivatives. However, one thing you always have to remember when calculating directional derivatives is you always want to work with a unit vector. It's kind of like a standardizing how long everything is. So this orange vector I just drew is the vector v. My first step is going to be to convert this into a unit vector u, the vector which just has length 1. And so the unit vector u, and to calculate that, u is going to be, we'll take the vector v and divide it by its length. And this vector has length 5. Right? 2 squared plus 1 squared is 5, and take the square root of that. And so in this case, this is going to be 2 over rad 5, 1 over rad 5. Right? That's the unit vector we want to work with. So to calculate the directional derivative, right, du of f is going to be df dx times u1 plus df dy times u2. Right, so the df dx, done that a couple of times, that's 2x y cubed. That's going to get multiplied by u1, that's 2 over rad 5, plus df dy, that's 3x squared y squared. u2 is that second component, so that's 1 over radical 5. And finally, we want to evaluate that at the point 3, negative 1. And so let's evaluate that at xy equals 3, negative 1. See, what do we get? Plugging in 3 and negative 1. In this first part, we'll have 2 times 3 is 6. The negative 1 cubed is negative 1. That's going to give us a negative 6 times 2. That's going to be a negative 12 over rad 5. Plus, so I've got 3x squared. That's 9. Y squared is 1. 3 times 9 times 1, that's 27. This is plus 27 over radical 5, which is, see, 27 minus 12 is 15. And so as you travel along this direction, right, how quickly is the height of this function changing? It's changing at this rate. And that's how you calculate a directional derivative. And we should do maybe at least one more. And switch colors. Let's say, let's calculate, let's do a couple directional derivatives. Let's calculate the directional derivative of the function, let's say f of x, y is equal to, let's say 5xy plus y squared at the point xy is equal to, let's say maybe 2, 1. Let's do this in multiple directions. So this is multiple problems rolled into one. In the directions, let's do v is equal to, let's do the direction maybe 2, 2. Let's also, just for fun, do the direction w equals 0, 1. All right. So to start off, the formula for a directional derivative. And first we have to make sure that we normalize our vectors. So maybe I'll switch colors for each one of these problems. So I'll do the first one kind of a greenish color. So for this color, the unit vector u, I'm going to take the vector v, divide it by its length, so I get a unit vector. Let's see, the length of this vector is, see, 2 squared plus 2 squared, that's 8. So we're going to have square root of 8. So this is going to be 2 over radical 8. 2 over radical 8. Radical 8, of course, is 2 rad 2. So if you wanted to, you could simplify this a bit more. It's 1 over rad 2, 1 over rad 2. And so for this directional derivative, du of f is equal to, remember the formula, it's df dx times u1 plus df dy times u2. So here, what's going to happen? Df dx, so x is the variable, y is a constant. And so we have 5xy, x is the variable, 5 and y are constants. Derivative of constant times x is that constant. So I have 5y times u1. u1 is this first component. So 5y times 1 over radical 2 plus df dy. So derivative of this with respect to y is going to be 5x plus 2y times the second component, which is again 1 over radical 2. And then you could evaluate it at this particular point by plugging these values in for x and y. And so at the point xy equals 2, 1, let's see, you're going to plug in 1 for y, so you'll get 5 over rad 2 plus, see, 5x plus 2y. It'll be 10 plus 2, which is 12, plus 12 over radical 2. So we're going to get 17 over radical 2. So that's the directional derivative in that direction. Of course, if you go in other directions, you're going to get other answers. Because there's lots of different directions you could travel in. Maybe I'll do this one in a blue color. And so first I need to make a unit vector. Now the interesting thing about this vector is, hey, it's already a unit vector, right? The length of 0, 1 is 0, 1. So that's nice. That's one less thing to worry about. So now if I calculate the directional derivative in this direction, something actually really interesting happens, which is why I wanted to do 2 directions for this problem. Right here I'm going to get df dx times 0 plus df dy times 1. What? Right, what's happening here? The 0 is going to cancel out the df dx. And so all we're left with is df dy times 1, just df dy. We get the partial derivative in the y direction. And you know what? This actually makes a lot of sense if you think about it. Geometrically speaking, where does the vector w point? Well, it's the vector 0, 1. W points in the y direction. So what this is telling us is something we actually already knew, but it's comforting, that if we want to calculate the directional derivative in the y direction, the answer is going to be the partial derivative with respect to y. And another fun thing to check on your own would be, what if you were calculating the directional derivative in the direction 1, 0? Right? Go ahead and verify that that also gives you the directional derivative df dx. And so directional derivatives, they're a little bit more complicated than partial derivatives, but they also agree with our earlier intuition in that case. And so now, directional derivatives empower you to calculate the derivative of a multivariable function in any direction. Thanks for listening.